So the thing that I've been thinking about at the moment, which I just thought I'd share at the start, is that a quote from a guy called Bernardo Kastrup, who is a Dutch philosopher. And in a video I was watching of him, he said that the subjectivity behind your eyes is the same subjectivity behind my eyes. So I'll put a link for the video where that comes from. But I just thought it was interesting. And then I was looking a little bit at his philosophy, and he argues basically that consciousness is the fundamental reality, and that we're all just sort of manifestations of one sort of larger mind, which I thought was interesting. So yeah, go have a look at some of his stuff. I think it's just cool to sort of encounter some of these ideas. I think his whole thing is what's called analytical idealism. So mind is fundamental rather than the physical universe. Anyway, so what we're talking about today though is sort of physical in some sense, or it's material. We're going to talk about the constant acceleration formulas, and we're going to derive three of them. So when we're talking about constant acceleration, there's basically four formulas that are useful when we're thinking about things accelerating at constant rates. And here they are. So we've got V equals U plus AT, S equals UT plus a half AT squared, V squared equals U squared plus 2AS, S equals a half U plus V times T. And all of these letters obviously represent numbers, and U represents the initial velocity, V is your final velocity, A is that constant acceleration that we're talking about, S is the displacement, different from position, so we'll talk about that a little bit, and T is obviously the time taken. Just a few caveats you need to be aware of when you're using these constant acceleration formulas. Firstly, we're talking about motion in a straight line, and we're talking about constant acceleration. We can't have acceleration, we can't use these formulas when the acceleration is changing. And I think acceleration's sort of poorly understood generally, but just quick recaps. Acceleration, you can sort of think of it as a sort of a speeding up or a slowing down. And remember, the units are things like meters per second every second. So imagine you're starting at rest, then you're accelerating at say 2 meters a second every second. So your velocity is increasing at 2 meters a second every second that passes. So that represents an acceleration. It's the rate of change of velocity. So what we're going to do is we're going to run through the first three proofs of the constant acceleration formulas, and then I'll leave the last one, as an exercise for you to give a go. Just to help you visualize acceleration, let's imagine that we've got some point P and it's moving to the right, and you'll see a sort of green arrow growing as it moves to the right. That green arrow is the velocity vector. And so if we think about this point P, as its velocity increases, that must mean that it's accelerating because there's a change in velocity. So that's what we're talking about. And the other thing just to note is that we're saying it's constantly accelerating. So for example, when I programmed this, it was at 1 meter a second every second, or whatever that translates to in computer world. So let's have a look at the first one, see if we can prove that V equals U plus AT. And this first one, I think we can actually understand intuitively once we work through the proof. We can start to understand why it's true. So the first thing to say is that acceleration is defined as the change in velocity over time. So I think we're hopefully familiar with that from the previous video. Then what we can say is we can multiply both sides by dt. And if that's a bit uncomfortable, I'll put a link below for why we're allowed to sort of treat that derivative as if it's actually a fraction. But basically, on the left-hand side then, I think you would agree, if you multiply both sides by dt, you'll get a dt equals dv. And then if you integrate over time, so if you take the integral from 0 to t of that acceleration, then that's going to be the left-hand side. And then you do the same thing on the right-hand side from your initial velocity, which is u, to your final velocity, which is v. Because remember, these are sort of representing our bounds. And so, we integrate and we get this. So that the integral from 0 to t of a dt is at, and the integral from u to v of dv is v minus u, using the fundamental theorem of calculus. And so what we can do from there is we can solve for v, and so we get v equals u plus at, which is what we were trying to show in the first place, right? Now that was all a bit abstract, that's sort of the formal proof, but I think we can understand this sort of intuitively if I was to say to you that the final velocity is equal to the initial velocity plus the acceleration times time. Now let's sort of think about that for a moment. Let's for a second assume that your initial velocity is 0 meters a second. If you wanted to work out, the velocity of some point P, well, it should sort of make sense that if you were to find that final velocity, you take the acceleration across the time that it took. Let's talk about an example. So imagine you're at starting at a velocity of 0 and you're accelerating at 2 meters a second every second. And let's say that you're doing that for 3 seconds. So if you started at 0 and you accelerate at 2 meters a second every second, so in the first second you'll have accelerated to 2 meters a second, in the second second you'll have accelerated to 4 meters a second, and then in the third second you'll have accelerated to 6 meters a second. So you can see that this idea of acceleration is clearly a change in velocity, and we can say, but based on this logic, that the velocity is equal to your final velocity, I should say, is equal to your initial velocity plus the acceleration times time. Okay, so hopefully you can sort of see where that logic comes from. If we look at the next thing, which would be the next formula, proof of S equals ut plus a half at squared. Now remember, S is this concept of displacement. Okay, and we'll talk more about that in a second when we get to the end, but here's how you would sort of prove this one. First thing you would say is that the velocity is defined as your change in position over time, which again we spoke about in that previous video. And so if you substitute V equals U plus AT, which we just proved 2 seconds ago, then you get the left-hand side equals U plus AT, or if you swap it around, the right-hand side equals U plus AT is equal to change in position over time, change in time. And so multiply both sides by dt. So you get dx equals U plus AT multiplied by that dt. And now we integrate. So if you integrate dx, you basically get x. So you integrate a small change in x, just gives you that quantity back, so it gives you x, and then you integrate the right-hand side, and we've done a bit of integration by now. You'll get this, so you get x equals ut plus a half at squared plus this constant of integration d. Okay, and then, so the final step, you're probably wondering, where does the s come in? And this is the tricky part, I think. The s comes in since s equals x minus d. Now that's a bit confusing, but we're saying s represents the displacement, right? So the displacement is basically this concept of, well, when I think of displacement, I think about running around athletics track. If I was to run around an athletics track, my distance, which is 400 meters long, if I was to run around it, my distance I would have traveled would be 400 meters. But by the time I get back to where I started, my displacement is actually 0. So that's just the concept of displacement. But in these terms, your displacement can be defined as s equals x minus d, where x is your position, and minus your final position minus your initial position, essentially. Okay, and so you're probably wondering, well, how does that get into here? Well, if you were to subtract d from both sides, you get x minus d, which is s. So I've just basically taken this constant of integration over to the other side and then set it equal to s, because it's actually equal to the displacement, and we need to be careful about that. So we get s equals ut plus a half at squared as our second constant acceleration formula. Cool, let's look at the last one, as he said, and then you can leave the fourth one as an exercise. So proof of v squared equals u squared plus 2as. So the first thing we might want to do is we're going to draw on some of the information before. We're going to set v equal to u plus at, because we know that. Rearrange to make t the subject. Okay, so if we rearrange to make t the subject, we'll get t equals v minus u on a. Just by rearranging that there. And I should point out, the reason we're doing this is because there's no time in this equation, right? The final velocity can be thought of as a function of the initial velocity, the acceleration, and the displacement. Okay, and not actually be in terms of time. So if we substitute into s, which was the second one we just proved, we're going to take this formula which we just proved, and we're going to put t in. So we're going to get that. I encourage you to get a pen and paper out. It feels like you'll feel quite accomplished to do this by hand, I think, because you've got the algebraic skills to do it, I hope. and multiply through by 2a. Now that's the tricky part. I suppose one thing you could look at is you've got a half a here. If you multiply that by 2a, on the left-hand side you get 2as, then you'll get 2u multiplied by v minus u, because you divide through by the a cancels out, and you've got that factor of 2 there. And yeah, here you'll get v minus u squared. And I'm just going to pause for a second. Oh, I'm not sure why I was worried about that. This is a squared, because I thought these ones would cancel out and then you multiply by a again, and then there would be an a back in there, which doesn't appear here. But no, it's right, because this is a squared. So yeah, that 2a will cancel out all the a's there, and you'll be left with this. And then you expand. So you expand this out and you'll get this, and then you've got some like terms. So on the right-hand side, you'll get 2uv minus 2u squared plus v squared minus 2uv plus u squared. 2uv minus 2uv, they cancel out. Minus 2u squared plus u squared is minus u squared. So we're just going to be left with v squared minus u squared on the right-hand side. And you rearrange it for v squared, and you get that v squared equals 2as. V squared equals u squared plus 2as rather. And so yeah, that's our constant acceleration formula proofs. Using those three, now that you sort of can see where they come from, I hope, at least algebraically you can see where they come from. See if you can prove that last one. Good luck with all your studies. Let me know how you're going. If there's anything I can help with, or if there's anything, any videos you want to see sort of animated as best I can, I'll be happy to do it. Good luck, and I'll see you soon.